Hey class, so to help you all cope with the sadness of no physics class today as you start spring break, I thought I'd make you a homework video that a few of you have been asking about. So what we have in this situation is we have three different objects, three different point masses is how we're going to treat them, as we're told here to treat them as particles, that are attached around this point P, and they're going to be rotated in two different ways. The first is being rotated about an axis that goes into the page through point P. So I can't really draw it on here since my iPad's two-dimensional, but going through this point into the page is our first axis, and then the second axis that we're asked about in part B is an axis like this that's perpendicular to the 2 meter or 2L length rod that runs in the plane of the image. So those are our two axes that we're going to be looking at. Okay? And so we're asked to determine in both situations what the total rotational kinetic energy is of the system when it's rotating with a speed of 1.4 radians per second, which is an angular or rotational speed. So, to remind ourselves, we know that the kinetic energy for something rotating is equal to 1/2 I omega squared. So it looks just like what it would look like for linear motion, but instead of mass we have rotational inertia, sometimes referred to as rotational mass, and instead of velocity we have angular velocity omega. Alright? So in order to solve for this, we're given omega straight away. We know what omega is for both situations. We can see that omega, at least in my problem here, is 1.4 radians per second. Rad per second. Hopefully your rad per second for spring break is quite high. And then the other thing we need to determine is what I is. And if you remember, I is equal to, for point masses, mr squared, m1 r1 squared plus m2 r2 squared plus m3 r3 squared, and so on until you've added up all of the individual masses in your system. So let's go ahead and break this down. So starting with part A, that's our axis going through point P, it becomes quite simple. You can see M1, if we start here, M1 is just 2M, R1 is just this length L. That's the perpendicular distance between our axis of rotation and our mass. So our I would be equal to, we got mass 1, which is 2M, multiplied by the distance L squared. Moving to the next one, here, we once again have 2m at a distance of L, 2m multiplied by L squared again. And then lastly, we have our third mass out here, which is at a distance of 2L away. So plus m at 2L squared. And just an interesting side note to observe here, so we can look and see we have 2m at a distance of L. Its inertia contribution when we multiply this out will be 2ml squared. Same thing here. But over here, the single mass m, so it's half the mass of the others, but twice the distance away, notice that its contribution to I is going to be 4ml squared. So it actually contributes twice as much rotational inertia as either of these do by themselves, or as much rotational inertia as these two added together. So interesting to observe. Anyway, so from there you have I, we already have omega, and so you should be able to figure out the kinetic energy for part E relatively easily with the values given to you. So if we move on then to part B, things get a little bit trickier. So now we're at part B, so I'm going to come over here, see if I can erase what we had going on over here. Look at that. So now our axis of rotation is here. Okay, so now when we're looking for our perpendicular distances, and we're going to sum them up for the masses, we start here. We have 2m once again, but now our L distance is the perpendicular distance. Its shortest distance to that axis of rotation would be there. Similarly for this mass, 2m, our distance would be this distance here, and then lastly our single m out here, it's still the same distance, 2L away. Okay, so what we're going to observe then, if this angle is theta here, then that distance for both of these is going to be L times the cosine, right? So if we go ahead to try to figure out what the I value is in part B, starting with this mass, it's going to be 2m multiplied by L cosine theta squared plus, then the next mass is also 2m times L cosine theta squared, and then lastly the one that I've made green is the same as what it was before, m times 2L squared. So once again, you should be able to determine what the kinetic energy is equal to based off of those values that you see there. So go ahead and try that out. Let me know if you have any questions, and yeah, have a great spring break.